So welcome everyone to the final in kind of our three-part series talk. This one looking at focusing on design for manufacturing and assembly, in particular looking at how we utilized it on Everton and the use of digital data. So I'm Darcy from Buro Happold. I'm a senior computational designer. I'm joined by John Lawton from Laing O-Rourke. John, do you want to just give yourself a bit of an introduction?
Yeah, cheers, Joe. Yeah, so as it says there, I'm from Laing O-Rourke, technical leader for Digital Engineering Solutions. Joe's kindly invited me to support some questions he has on this presentation, specifically around the Everton project and how we've used DFMA in the solution and the areas there. So I have a generally background of 10 years in digital construction with Laing O-Rourke, prior to that an architectural designer. So I think a good fit for this, and thanks, Joe. And
great. A bit of background, I suppose, from Buro Happold. We have offices all across the globe. We're an engineering and consultants, primarily working within the built environment. Our projects likewise are international and in most countries. Sectors we span across lots, although obviously focusing on sports and entertainment in relation to stadium today, talking about Everton. And yeah, so what kind of going to go through is looking into DFMA, how it relates to stadiums, how on Everton we used it and combined it with digital data, and where this might lead to projects in the future. So a bit of background. Everton Stadium, I believe, once it's constructed, will be the first precast stadium. I mean, obviously, most stadiums might have some form of precast involved in their construction. However, on Everton, we've fully embraced precast, in particular kind of DFMA use with precast. The stadium itself, if you haven't already seen, based on the docks, technically the kind of the precast use is a hybrid system of precast elements and in situ concrete, using Laing O-Rourke's DFMA system of lattice planks and twin walls, along with precast columns and beams. The north and south is on the existing wharfs of the docks, has to interface with the dock walls as well, and is a steel frame using their lattice planks and twin wall systems. The east and west is situated within the dock itself, and it is primarily of concrete with precast concrete columns with lattice slabs as well and twin wall. Above both the north and south is long spanning trusses, which I won't go into detail here, and the east and west is cantilevering trusses of a steel frame. Just to give you kind of a brief description of the DFMA, well, a bit more detail on the DFMA items implemented on Everton. The lattice planks, which is a precast biscuit with a girder system, completed on site with an in situ topping and reinforcement. It's also precast beams, some of which include notches enabled to stitching into the lattice slab itself. Twin wall system, similar to the lattice planks, is precast biscuits with a girder system between them, which is then completed with in situ fill and stitching reinforcement between the different planks, and also columns as well, precast columns. So DFMA, what is it? And kind of a bit of context around it. So DFMA is designed for manufacture and assembly. Typically, this is a process used extensively in other industries and fields where mass production is critical, such as automotive product design and aeronautical. But it has been starting to come into the construction industry as of late. I think it has started in the 70s, but recently it's starting to make, there's a bigger push for it going forward. So DFMA is actually a combination of two different processes, design for manufacture and design for assembly. So if we take, say, an example of a thin steel wire product that we're wanting to produce in order to join pieces of paper together. If you consider it from a manufacturing point of view, you might end up with a paperclip. The paperclip itself was invented turn of the 19th to 20th century. There was lots of people came up with different designs. There was one Norwegian inventor who invented something that, whilst functionally worked, it actually couldn't be produced. Whereas the paperclip that we all know today actually largely hasn't changed in over 100 years because the process of producing it was so efficient and driven it so much. Likewise, if you were to look at that steel wire in a different way from an assembly point of view, you might get to the staple. Again, same time it was kind of created and formed. One of the original kind of staplers, McGill's single stroke stapler press, you had to manually load your staple, hit the top, and it then joined. Whereas if you, I imagine everyone has a stapler to hand at the moment. It's developed a lot, and the assembly of that staple, as you know, has developed to facilitate, a very quick assembly of those staples. The video clip here I've included is the unofficial world record of how many staples can you put in a piece of paper in 10 seconds, which is 60. If anyone fancies trying to beat it, please feel free. So that is, and I suppose an important thing about DFMA is trying to bring these two approaches together in order to then create a product which reflects the needs of both, whilst also bearing in mind the original design intent. So DFMA in construction, I've kind of drawn up a Venn diagram here of design, manufacture, and assembly, but for the purposes of, I suppose, construction, our aim is to end up with something that's built. So actually, design should actually be housed within assembly and manufacture, as if you have a design and you can't assemble it or manufacture it, then you won't have something to construct. So looking at where the typical materials of construction fall into that, you might say that in situ concrete is on the assembly side of things, with precast being more on the manufacture, although granted, aspects of it you need to be able to install it and assemble it on site, but I feel it lies more with manufacture. Steel is typically more assembly based, likewise as timber, although you do have the likes of cross-laminated timber, CLT, which requires quite an extensive manufacturing process, and then implications on its own assembly. And within that central section there is DFMA. And so where you're having, and that's what we're going to focus on. So DFMA and stadiums, is this anything new? I'd potentially argue it's not, or at least not within kind of the modern era of stadiums. Here on screen are examples of precast terracing, of which is now the default for kind of bowls within stadiums, and has been developed over the years, and that the process and involvement, typically the final design and production is carried out by a specialist subcontractor to create these repeatable units. Again, going back to that kind of mass reproduction, which is kind of where DFMA has its benefits. But the kind of the design of it, in the design phase, we would require the information from the specialist contractors as to how they are wanting to to make it how it's then going to be installed? What are the limitations? And over the years, because we've been involved in lots of stadium projects, we've managed to build up a knowledge and an understanding of those likely methods of how it will be manufactured and how it will be installed, such that actually the point of kind of transfer of the information across to the contractor, the specialist contractor, to carry out the design is a reasonably smooth process now, and doesn't require significant changes in the original design intent, because we are very much aware of what the desired design from a manufacturer and assembly point of view are, i.e. we don't make a terrace unit that is so large it can't be installed because you can't get a big enough crane, or we don't make terrace units so long that they can't be taken to site because they can't fit on a truck. So how is DFMA kind of adopted on Everton? Typically, DFMA adoption on projects happens towards the end of stage 4. In blue here, you have the kind of rebirth design stages 3 to 4. There's then typically an overlap with, in green, the construction phase, of which you get towards the end of the design. You then transfer information across to the contractor, and then they would start carrying out their processes and understanding how they could start doing their manufacturing and construction processes. The ability, so what I have on screen here are 2 S-curves, one which represents the ability to influence or change the design, which is in orange. The other is in purple, is the impact of that change, whether that's on the project and the design, whether that's the cost, or whether that's on program. So you can see by having DFMA starting its process towards the end of the design, you end up with it having any changes that might need to be incorporated due to using DFMA have a low ability to change. And anything that is then subsequently changed has a high impact on that project. And so it can then be difficult for the adoption and the use of DFMA to be embraced. On Everton, we looked to use kind of our digital data, our computational expertise and methods to allow that process of adopting DFMA to be brought forward. So for that, we used our Revit model, our design, our intent, and extracted the information from that and pulled it across into Grasshopper, which is a visual-based scripting program within Rhino, an environment that can handle geometry and data very efficiently. Working closely with Laing O-Rourke, we are able to distill their key principles that drive their processes for manufacture and then assembly, and create objects, the plank objects that they ultimately want in order to then carry out their design and embed their information. In that process as well, we then populated those objects with our design intent and created a parallel Revit model, a precast model for them to then use to carry on their processes. As a result, this is kind of how the adoption of Everton, of DFMA on Everton looked, whereby we had this parallel model. We were able to engage with Laing O-Rourke's earlier, to feed information across to them earlier, to allow them to start their processes and understanding of where the design was getting to, all while using the scripts that we developed, allowed the design to continue to develop during stage 4 without abortive work happening. You can see here the share of several Revit models across to Laing O-Rourke's whilst the design was happening and changes were still happening. So in the end, I feel as though that allowed us to provide the information earlier to them and facilitated them doing their processes quicker, and hopefully relieved some of the pressure on the tight construction timeline. And again, going back to those S-curves, you can see that now, due to that earlier adoption, we have an improved ability to make changes within the design with a reduced impact on any negative kind of implications for the project, i.e. cost and program. John, I was going to pose you this question. What are the main benefits Laing O-Rourke have seen from this early integration of DFMA on Everton? If you're still there, John. Okay, it would appear John's dropped off. I suppose from my point of view, while not privy to kind of all of the workings of Lang's, I think one of the benefits they had was us being able to provide them with these Revit models, these objects earlier, facilitated them with their costing and understanding and mitigating against the risk of unknown. We were able to tell them, you know, how roughly how many planks they were going to need in their systems. Here he is, which mitigates against some of their risk. John, glad to see you've joined us again.
Yeah, sorry, I had the internet challenges, so I do apologise for that one. Okay, so you come on to, yeah, what the main benefits to Laing O-Rourke have seen. Yeah, I think Laing O-Rourke have a strong history in DFMA, and we started in the precast concrete arena for our structural elements, and we've done that for lots of our schemes. The primary drivers for us is looking at improved quality, looking at cost certainty, and going down this route also provides us a program improvement. So we wanted to drive that onto the Everton project, arguably, and bring it into the solution. So then we look to optimize the scheme in that capacity. And the benefit we get from that means we can get an earlier indication of costs. So we understand the products we're going to use, we understand the cost of those products, and bring it into the scheme. And again, with that aspect and going the digital route, we can look at reducing errors and the coordination of the activities through there, and the constructability into the scheme, the detail we need for manufacture, and the information that we need to deliver it. We can then help and actually communicate that to Joe and the team at Buro to help them actually design the solution with that in mind, and optimize the arrangements of the lattice solution so we can make sure they connect with the structure correctly. We can align that with the building services so we can get the routes through for any penetrations to service the building. And from our side, it provides greater surety, and hopefully that's something we'd like to pass on for delivery of all our projects for all our clients. So that was the big driver from our perspective in Laing O-Rourke.
Okay, great. From your Happold's point of view, why did we want to do more with DFMA? Why did we want to get involved in this process? And why did we choose to do it kind of using these digital computational methods? So our Revit model, our design intent, has hundreds of objects, floor objects, beams, walls, and columns, and to transfer that across to the requirements for the manufacturer, that then resulted in thousands of lattice planks. So to do that manually would be a very slow and arduous process, particularly if you were having to do that multiple times as you wanted to start it earlier. So doing it by scripting it allowed us to form a script to carry out this action for us. Also, with the thousands of lattice planks, there's also thousands of voids as well within those to allow for, as John mentioned, the MEP openings to make sure that we have full coordination with them, but also in the regions of steel, we are having to allow for openings around the steel columns coming through and the bracing elements as well. Likewise, creating the objects for the upstands and beams, less of a kind of computation required there because there's less of a differential between the number of manufactured objects that are required to represent the number of design objects. The walls, due to the kind of the arrangements and breaking them down into the twin wall panels, obviously there's some more there required because you can't do an entire wall and produce that, take that to site. So that was, we again drove that to a degree with some computation, and the columns as well. And since we'd then gone through the process of creating all of these objects, it then made sense to not just provide a dumb placeholder object to Laing O-Rourke's, but to embed the rest of the design intent. So taking the reinforcement from the slabs and embedding it within the lattice planks, taking the reinforcement quantities for the beams and populating it. The column, the walls as well, embedding their reinforcement, and likewise with the columns. And as part of that process, we were seeing, there being efficiencies there in helping us, and equally Laing O-Rourke were also wanting to maximize efficiencies on this project. So while there is a permanent design which we are needing to then embed in the objects, there is also then the temporary design. So we worked closely with Laing O-Rourke's to understand what their temporary requirements were for assembling all of these planks on site. We were able to then distill this essentially into a load table, and then because we have the objects, we know where the plank is, and we know where its supporting beams are, we can then understand the spans that each of the plank has to deal with and cross-check that against the temporary works load table to then understand, oh, this needs to be have a temporary works design of number 2, and embed that in the object. Whilst doing that, we then also outputted that process. So this was carried out using a different script, but allowed us to then understand for every plank what its span is and produce a drawing for that, and feed that across to Laing O-Rourke's in order to facilitate them checking their temporary works design more efficiently and quicker. Again, kind of going through the process of this was required a lot of collaboration between ourselves and Laing O-Rourke's to understand their requirements and limit and parameters that are critical to their DFMA system, and how that relates to our design, and where we can incorporate those requirements with a minimal impact on the design. So looking at the lattice planks, I suppose one thing, having gone through this process, aware of and learned, is that will actually, to facilitate a smoother transition across to DFMA, there's some key things which are beneficial to know, such as their maximum plank length due to the manufacture and also kind of bringing it to site. This, if you have column grids which are less than 12 meters, then you automatically fall within their realms of what they can produce for DFMA in terms of where you're dealing with precast steel, requiring a minimum bearing of the plank onto the steel beam of 75 millimeters. Well, where you have two planks coming onto a beam, that effectively means that you need to have a minimum beam width of 160 millimeters. So if we're able to be mindful of that when we're then designing our primary and secondary beam systems, to have at least a flange width of 160 millimeters, then we're not then going to enter into problems when Laing O-Rourkes have to carry out their temporary design works of whether the plank is then stable installed in the temporary condition. Likewise, understanding some of the key parameters and drivers for the beams, although granted, because these are the beams aren't discretized up as much, it's not really a driver that influences too much could influence in the early stage of the design. With the twin walls, the limitations of what they can produce in terms of thickness, if we're able to be aware of that limit of around about 400 millimeters, so that we don't we can, our designs, our course layouts, where our stair arrangements consider that, it will then again facilitate an easier transition across to DFMA. One other thing, I suppose, I haven't got here listed here, but there's the reinforcement sizes and spacings, which kind of implicitly, based on those, you can then have a maximum force and stress that a wall can easily take. If we are conscious of that at an early stage, we then don't end up having to put significant amount of reinforcement in the in situ part of the twin wall to facilitate where you have the joints, the force being able to be transferred between planks. And likewise columns, I mean, here I've highlighted kind of nominal column dimensions, of which anyway we would look to kind of be within the realms of them. So again, John, looking at collaboration, where do you see model share and data collaboration between consultants and yourselves, contractors, looking forward?
Yeah, it's a good point. I think going DFMA as a product-based solution is really important to us as an organisation. But then looking at the digital technologies we use, and taking it from design to the manufacturing detailing stage, and we're going 3D and putting data in the 3D models is really important to improve that exchange, the data exchange. That does provide us the opportunity to reduce the manual interpretation. If you're getting a drawing and someone's got to read that drawing, interpret it, and then put it into another computer system for making the products, can we remove that time, the chance of error creeping into that step as well? Models provide us a way of reducing those issues for us, which is good. But getting the parameters in, like Joe just described, into the object, it makes that really efficient for our manufacturing processes. And we can take that into actually making the products and then taking it onto site as well. So then we bring that back out. So our manufacturing detailing do produce their own 3D model then of the manufactured element that we can give back to Joe and the team to ensure this is the product we're going to make and here's a 3D of it. And then you can then compare and contrast that with the original design intent and go, okay, does that represent what we're going to construct, and does that represent my design? Making sure all the holes are in the right place, making sure the reinforcements doesn't clash with other elements then that we would produce as part of the scheme. And it means it is really important for us. Our key now in Laing O-Rourke is broadening the product set, taking it out of maybe precast and taking it out of structural elements and going broader to architectural elements, facades, building services, making like packaged plant rooms, constructing plant rooms off-site and then bringing them pre-configured that we can just plug and play and connect on site rather than having lots of labour on the construction site there, actually increasing risk because people, health and safety on site and things like that, reducing the numbers, reducing working at height and things like that. So it's a big plus for us.
Okay, that's interesting, I suppose. I mean, I think MEP in particular has seen a direction of there's bits of kits, there's modular bits of kits which can be put together, and that's I think my colleagues are very much aware of that becoming a bigger thing. I suppose almost it might be that we see that becoming more of a thing from a structural point of view, where well, it's almost there, I suppose. Just at the moment, you've got loads of options in terms of what reinforcement thickness, and I suppose whether we look to, well, are there more efficiencies in which of those options you produce, and should that be brought forward into the design so that you, rather than us making lots of really large columns, we make a particular size of column with a particular reinforcement, which is more efficient for you to produce?
Yeah, providing repeatability is better in the manufacturing process if we can create a mold that will repeat many times. If that means we slightly overspec it so it covers more scenarios, that actually is better for us for program and cost longer term as a holistic view. Rather than having every column is bespoke, every solution is bespoke. And I think it brings into that idea of like uniqueness in design. How do you keep uniqueness? How do you not stifle design having standard products? When you bring it back to like the world of Lego, you know, the variety you can construct with Lego, but it's based on like standard Lego sizes, Lego products. We've got to increase the options available to us so we can be more creative.
Yeah. Okay, thanks. And then I suppose moving towards a finish, one of the outcomes that I found from us having created these objects and embedding the data in them from the design intent and also then the temporary works requirements, was able to then get an understanding of, this is looking at one of the levels in the north and south for the lattice, is where is the design governed, and how much of it is governed by any particular aspect. I mean, you can see here that the vast majority of the design is equally governed by a permanent condition designed for our design, and then the installation kind of temporary condition, which I think this probably shows as much as you could hope to get. I mean, if the corner stands on Everton are very complex, are very difficult. There's not that much repeatable grid set out. It varies quite a lot. So in order to achieve, you know, this high proportion of 40% kind of equally being governed by the temporary and the permanent design, I think is quite impressive. To end up with a design where you're, you know, almost completely equal, you have something that looks very different. You'll end up with almost being completely governed by the architecture, or the visual of the design has to then compromise significantly. So I wonder whether we've managed to achieve something that is for the architecture, the challenging architecture that's being achieved. We've managed to get something that's very efficient, both from a permanent design and a temporary design. And then I suppose, well, you slightly touched on it before, John, in terms of where Laing O-Rourke's looking to go, but anything more to add on where you're going to try and push the boundaries?
Yeah, I think we're looking at putting a title to it called product-based building solutions, and aiming that, like say, increase the product set, but then taking that into configuration. So a little bit more on the scripting approach you talked about before, Joe, on the algorithms to optimize the layouts, but doing that not just based on one product, but between how different products interact, and then bringing the intelligence there, and then we can start optimizing the design and the solutions, arguably with artificial intelligence. You put the knowledge into the systems, and you can start then seeing what is the correct solution in this scenario based on life cycle attributes, based on design, environmental information, what's the most optimal solution in that sense, from construction to how we install it, to even down to the labor. Can we, when we do install it, what type of injuries would they get from the positions they're going to be installing the products? Can we minimize that to, from a well-being point of view of our staff and things like that as well? And we could take that into actually the maintenance side of things as well. it's very new. It's where we're looking to go. So can we achieve this? So taking what we've done here, linking it to configurator to optimize design, and then take that with then the pushing the boundaries with this artificial intelligence on elements there. So we get the information earlier based on decisions. So it's quite exciting in the digital world. It's quite research and development based. We'd like to think we bring some of that to our projects as we develop it. So and we do some discovery like we've got here. That I think the algorithmic scripting you've done here, Joe, I think has been really impressive to see from Laing O-Rourke's point of view as well. So.
Yeah, and I think we're already looking to the next projects we're working on, and whether yourselves are going to be involved in them, and how we can take what we've learned from Everton and apply it to that next project. I think collectively we've done a lot of learning on the use of DFMA and this new way of utilizing data to facilitate benefits on both sides, and how best we can then take the next step and use it more. And then I suppose kind of to summarize, digital data on Everton I find has aided with the design. It has required a lot of collaboration between the design team and the contractors to understand the intricacies and the detail which can govern a lot of how something is manufactured and assembled. But by bringing that forward and kind of embracing it, it's kind of balancing within the design the requirements, the focus on architecture, the focus on engineering, and the focus on construction, to hopefully produce a design that's much more holistic and kind of better because of that. And as just said, kind of looking to hopefully develop that more on future projects. I see there's a question or two that's come through. One from John McGovern, who's on the call from Laing O-Rourke's. DFMA facade elements improve certainty of envelope completion with greater quality using factory manufactured elements delivered and assembled much quicker than a traditional hand-laid brick. So that's in reference, for those that haven't seen, that the facade on Everton is a series of brick-laid lifts, which we're looking at using kind of, as John mentioned, a precast system rather than every brick being hand laid. It'll be interesting to see how see that in the factory kind of being manufactured. Definitely. Is there any other questions that people would like to ask? I mean, I do notice that we have quite a few of the architects on the call who worked on Everton with us. Does anyone want to give their point of view on how they found, I suppose, although I think the architects weren't necessarily involved too much in kind of how we did things digitally, but the impact of kind of us embracing DFMA earlier on the project? No, okay, fair enough.
Yeah, hiya, Joe. Can you hear me?
Yeah, can you hear you, Andy?
Yeah, no, just one thing I was just thinking of. And so, I mean, with all this, is it correct to say then that it basically it looks like it needs a lot more work kind of in the office in order to make it easier on site? Is that, yeah? I mean, maybe you could sort of talk through that with John in terms of, I mean, how much more work do you think is actually needed to make it easier on site?
Well, I think because we've gone into much more detail from a design point of view of understanding what ultimately will be constructed on site, the individual objects, we've been able to thrash through and understand the details and gain more of an appreciation for those details, which I feel inevitably will see benefits of time saving on site. I mean, I think one of the main drivers for using the DFMA is program based on site and limiting that much as possible. and us being able to understand, we've, I suppose, almost really we've digitally created what will be there on site, and so can then understand how that can come together much better, rather than almost it's a dry run of how it will be constructed.
Yeah,
it's like an informed construction solution, isn't it? And what we're seeing is the time's still there, but we're taking the activity away from the site at the cold face into the factory conditions. So, we can improve quality of the products in that scenario, and you can manage how people go to work in a more controlled environment in that way. So we do then see the benefit of site time delivery is reduced, but we still have to produce the actual products in the factory. So it's just transferring that for us, and we did see the benefit in that the overall process of program and quality.
Possibly even more beneficial if a club was staying in the same location, and they were one of those examples where they go and play at another ground for like a year or two. The quicker that you can do the work on site, the less time they've got to spend away.
Yeah. Yes, their scheme can be up and running quicker.
Yeah. Thanks, guys.
Okay. If there's no other questions, then thank you everyone for attending. Hope you found it informative and useful.